Section 1 Introduction. We're here to talk about large language models, LLMs, which have shown great promise in a variety of language tasks. These models have become increasingly effective due to advancements in large-scale training methods and data collection. As a result, these models have grown in size and have shown improved performance, demonstrating their ability to learn in context and be used for various language tasks without needing to update parameters for specific tasks. However, there's a catch: the larger the model, the higher the cost to deploy it. Over the past few years, the size of these models has grown exponentially. For instance, the model size has increased by 1,588 times from BERT large, 340 million, to PaLM, 540 billion. Without improving the efficiency of these models, the cost and time it takes to make inferences will skyrocket. This is where quantization comes in. Quantization is a technique that reduces the size of the model and speeds up inference by approximating floating point numbers with numbers of smaller precision. This technique has been shown to be effective in speeding up the inference of neural network models, particularly in tasks related to natural language generation, such as machine translation and understanding. However, the use of weight-only quantization in large language models is still a relatively unexplored area. Existing methods often involve complex and costly procedures, such as additional quantization-aware training, CAT, and/or calibration on additional data. These methods often compromise either speed or accuracy. To address this challenge more effectively, we're focusing on a simple weight-only quantization method that doesn't require additional training. This method has several advantages. It maintains accuracy because its underlying numerical computation is done in floating point precision. It can be used for various hardware and GPU architectures without needing specific hardware instructions, and it avoids expensive additional training steps. Our research questions are: how can we effectively use this low-bit quantization without losing accuracy, and how can we efficiently implement a general matrix-to-matrix multiplication, GEM, that accepts different types on modern GPS? In this paper, we make several contributions. 1. We provide a comprehensive analysis of the quantization behaviors on LLMs, investigating the impact of applying low-bit quantization, down to 3 bits, on LLM accuracy. 2. We propose a fine-grained quantization algorithm that incorporates group-wise quantization and adaptive selection of granularity. This approach helps preserve the original floating point precision accuracy even when there is loss due to quantization. 3. We implement highly efficient GPU kernels and conduct a thorough performance analysis, considering different batch sizes and context lengths. This analysis allows us to identify the optimal utilization of the proposed approach on real GPUs. 4. We demonstrate the effectiveness of the proposed method by applying it to a large-scale open-source dense transformer model called OPT. With its 175 billion parameters and internal mixture of experts, models utilizing optimized GPU kernels, our method enables deployment of the 175 billion parameter model on only 2 GPUs, resulting in a significant reduction of overhead and cost by 64%. Moreover, our method achieves 3.65 times higher throughput on the same number of GPUs. In summary, our work advances the understanding of quantization behaviors in LLMs, proposes an effective quantization algorithm, optimizes GPU implementation, and demonstrates the practical benefits in terms of reduced resource requirements and improved inference throughput. Section Summary. Large language models, LLMs, have become increasingly powerful in various language tasks, but their large size poses challenges in terms of deployment cost and inference efficiency. This paper explores weight-only quantization as a compression technique to reduce model size and speed up inference without compromising accuracy. The authors propose a fine-grained quantization algorithm and highly efficient GPU kernels, demonstrating significant reductions in overhead and cost, as well as improved inference throughput. Section 2 Background. Challenges of quantizing LLMs. In this section, we'll discuss the challenges we face when trying to quantify large language models, LLMs. 2.1 The fundamental challenges of inferencing generative LLMs. One of the main issues we encounter is the increased communication overhead. When we're performing inference with tensor parallelism, we need to issue an all-reduce after each attention and feed-forward neural network, FFN, block. Even though technologies like NVLink and NCCL have significantly improved GPU to GPU communication, we still aim to use as few GPUs as possible to reduce this overhead. Another challenge is dealing with large weights and small activations. As the model size increases, the matrix multiplication in the decoding phase of LLMs becomes a bottleneck due to memory bandwidth. The weights usually dominate the memory traffic as the activations tend to have only a few tokens once the context has been used to generate the key value, KV, attention caches. As the number of parameters increases, the amount of data that needs to be moved from the high bandwidth memory, HBM, to the GPU cores also increases, putting more pressure on the memory subsystem. Since computation is faster than memory in modern processors, it's desirable to reduce the memory bottleneck. Therefore, it's crucial to reduce the memory footprint. 2.2 Challenges with quantization. Quantization is a hot research topic aimed at speeding up inference and reducing the memory footprint of LLMs. However, it's not without its challenges. There's no single method that can maintain accuracy and improve efficiency simultaneously without introducing complex procedures for conversion and execution of an inference. Maintaining good accuracy when applying quantization to LLMs is difficult. Simple quantization methods can significantly reduce accuracy compared to the original models. This is partly due to outliers in the activation, based on previous studies. Some proposed methods to address this issue involve handling the outliers separately in floating point arithmetic or shifting the multiplier from the activations to the model weights. Achieving high efficiency is also challenging. Even if some algorithms can maintain the accuracy of the original floating point models, implementing these methods efficiently in reality is not straightforward. This often requires special kernel implementations on GPUs. For instance, some methods can achieve good accuracy with quantization, but the efficiency improvement is marginal. Also, some methods do not provide efficient inference kernels for batch sizes larger than 1. However, we note that our efficient GPU kernels can be used with weights quantized by these methods, allowing us to benefit from the speed of our kernels and the accuracy of these methods. To address the issues of accuracy drop and runtime inefficiency, several studies have been proposed. These approaches often require complex and costly procedures, especially when calibrating for a specific target task dataset. Some methods use additional knowledge distillation steps to recover the accuracy drop from quantization. Others use binary coding quantization and perform iterative numerical optimization to find the best binary coding scheme for a given model and task, which is not trivial. Some use optimal brain quantization, OBQ, to maintain the accuracy of the original floating point model by shuffling the model weights based on the approximated second-order Hessian matrix information. All these approaches introduce non-trivial and dataset-specific algorithmic procedures. Notably, the cost of these algorithms increases with the size of the base models. In this work, our aim is to find a scalable, accurate, and efficient quantization method that doesn't introduce additional costs for model conversion. Section Summary. Quantizing large language models, LLMs, poses challenges such as increased communication overhead and large weights with small activations. While quantization methods exist to reduce memory footprint and accelerate inference, maintaining accuracy and efficiency simultaneously remains difficult. Existing approaches introduce complex procedures and require target task-specific datasets, making them expensive and non-scalable. The goal of this work is to develop a quantization method that is accurate, efficient, and scalable without additional model conversion costs. Section 3. Designing quantization methods for LLMs, adaptive fine-grained quantization. In this section, we're going to delve into the world of quantization methods for large language models, LLMs, specifically focusing on adaptive fine-grained quantization. We've noticed some issues in LLM quantization that could potentially degrade the quality of the model, especially when it comes to the range of quantization. We've taken a deep dive into these issues and have been brainstorming ways to mitigate them while still maintaining effective control over the quantization range. Based on our analysis, we've come up with a heuristic algorithm that can automatically determine the best range for quantization. Let's start with the basics of our quantization methodology. We've been experimenting with two different techniques that focus on making the quantized range as uniform as possible. The first technique we tried was linear quantization. This method evenly maps quantized integer values to their original float values. The second technique we explored was log-based quantization, which maps both integer and float ranges on a logarithmic scale. We applied these techniques column-wise to see how the uniformity of quantization affects the accuracy of the model. We've included detailed explanations of these two techniques in Appendix A. We compared the performance of these two techniques when applied to feed-forward network, FFN, layers using low bits. We found that for 3 and 4 bits, both techniques performed similarly. However, when we used 2-bit quantization, the accuracy of the log-scale quantization significantly decreased. Given these results and the fact that linear quantization is computationally simpler, we decided to use uniform quantization for all our future experiments. Next, we looked at the numerical distribution of model weights to determine the best quantization approach. We found that the distribution of model weights generally follows a normal distribution centered around 0. However, in some cases, outliers can skew the weight distribution, which could potentially lead to an inaccurate quantization range. Considering these observations and the efficiency of implementation, we decided to use symmetric quantization around 0. Section Summary. In this section, the authors discuss the challenges and potential issues related to quantization in LLMs. They propose a heuristic algorithm to automatically determine the appropriate quantization range and suggest using uniform quantization for simplicity. They also analyze the weight parameter distribution and choose to employ symmetric quantization around 0 based on their observations and implementation efficiency. Section 3.2 Granularity of Quantization. In this section, we'll delve into the importance of quantization granularity in our algorithm design. This aspect is crucial because it directly impacts the efficiency of computation and memory usage. Typically, we use one quantization scale per tensor or one per each tensor column. However, to keep the quantized values as close as possible to the original numerical values, it's better to have smaller groups of parameters sharing scales. This is because outliers can significantly distort the data, reducing the precision of quantization, especially for smaller numerical values. We've noticed a considerable drop in performance when using matrix-wise quantization compared to column-wise quantization across different layers, as shown in Appendix B. Therefore, we've chosen column-wise quantization as our baseline for experiments. But even with this approach, we've seen instances of severe performance degradation in large language models, LLMs, especially when there are outliers in the model weights. We've observed a relationship between the mean squared error, MSE, of quantized values and the translation BLEU scores as we change the group size in the OPT30B model. As we increase granularity, the MSE values slowly increase, but the model's ability to score on the task BLEU score rapidly deteriorates beyond a certain point. Therefore, it's vital to find the best granularity for each matrix to maintain task performance while maximizing the size of the parameter groups sharing scales. Upon further investigation into the severe performance degradation of a quantized model, we found that adjusting the granularity of just 4 specific matrices out of the 288 quantized matrices could rectify the issue. Simply doubling the granularity of these 4 matrices allowed us to recover over 94% of the lost accuracy. Based on this finding, we've developed a simple rule of thumb method to assign different granularities to different model weight matrices. When quantizing a matrix, we start with column-wise quantization and calculate the range of values that need to be quantized. We then have the quantization group size and calculate the range for each group. If the new range divided by the old range is greater than a certain threshold, alpha, we have the quantization group size again. We repeat this process until the difference in quantization ranges between 2 granularities becomes smaller than alpha. We've seen the impact of adaptive group size on BLEU scores and model sizes in gigabytes, GB. With our adaptive fine-grained quantization approach, the BLEU score difference is only a marginal 0.1%, while the model size is reduced to just 26% of the original FP16 model size. Section Summary. The granularity of quantization is a crucial aspect of the quantization algorithm, as it affects computation efficiency and memory consumption. While it is typical to have one quantization scale per tensor or column, smaller groups of parameters sharing scales are desirable to maintain a close approximation of the original values. Catastrophic collapse in model performance can occur with matrix-wise quantization, but adjusting the granularity of specific matrices can recover lost accuracy. Adaptive fine-grained quantization, achieved through a heuristic-based method, allows for a marginal difference in performance while significantly reducing the model size. Section 4.1 Experimental Setup. In this section, we'll discuss the experimental setup we used to conduct our latency and throughput tests. We used NVIDIA A100SX M4 GPS housed within a Docker container running Ubuntu 20.04 and CUDA 11.8. We compiled all our code using NVCC 11.8.89 and GCC per gram++ 9.3. For these experiments, we used a modified version of the open-source Faster Transformer 1 versus 5.3. We tested our setup using various open-source language tasks, including Lambda, HelloSwag, PIQA, Wino Grande, OpenBookQA, RTE, COPA, and WMT machine translation tasks. For the MO models, we used a multilingual machine translation task that covers 10 language translation directions from and into English. We used a 128,000 sub-word vocabulary, built with the SentencePiece library. To evaluate the accuracy of our models, we used Soccer BLEU on the detokenized output. For the dense model experiments, we used various open-source large language models that share a similar architecture, which consists of decoder only with multiple transformer layers. These models include GPT-2XL, OPT, and OPT-IML, with the number of model parameters ranging from 1.5 billion to 175 billion. For our MO model experiments, we used internal pre-trained MO models with a few modifications to the transformer model architecture. These modifications include a deep encoder consisting of 24 transformer layers and a shallow decoder comprising 12 transformer layers, adoption of transformer with untied positional encoding, TUP, instead of the conventional sinusoidal positional embedding, and implementation of pre-layer normalization. We also employed top-1 learned gating and an MO layer with 32 experts at every other layer, specifically the even-numbered layers. We applied jittering noise, balancing loss, and gating dropout to prevent overfitting and improve regularization. We used the kernel implementations developed by Cutlass to create efficient kernels for fused dequantization and matrix multiplication. These kernels can process either FP16 or BF16 activations, a vector of scales of the same data type as the activation, and int8 or int4 weights. The kernels dequantize the weights to match the data type of the activation and perform floating point tensor core math. The final output of the kernel is also of the same data type as the input activation. To support multiple scaling factors for each column, we extended these kernels to process a matrix of scales, enabling us to implement int4 block quantization kernels. We set the block size to 64 for all performance analyses below, since it matches the k-tile size of our fused GEM plus dequantized kernels. In compute-bound cases such as an encoder or the context creation phase of GPT, the conversions from integer to float bottlenecks are kernels, rather than tensor core math. As a result, our weight-only quantization GEMMs slower than equivalent FP16 x FP16 GEMMs in compute-bound cases but offer significant speedup in memory-bound cases. We argue that this kernel is useful because large language models usually spend more time in the memory-bound decoding phase than in the compute-bound context creation phase, especially when the output sequence length is long. Also, large language models are typically served with small batch sizes in most practical cases, which puts significant pressure on the memory system during matrix multiplication as the weights need to be read from the GPU's HBM. However, our kernel utilizes int4 compression, which reduces the number of bytes needed to load the weights by up to 4x. For our quantization method, all quantization experiments have one scaling factor for each column of the weight matrix, unless a block size B is specified. In that case, each contiguous block of B elements in a given column has its own scaling factor. This means we have multiple scaling factors per column. Section summary. The experimental setup involved using NVIDIA A100S XM4 GPUs inside a Docker container running Ubuntu 20.04 and CUDA 11.8, with code compiled using NVCC 11.8.89 and GCC program++ 9.3. The experiments utilized a modified version of Faster Transformer 1 versus 5.3 and various open-source language tasks and datasets. For the dense models, GPT-2XL, 1.5B, OPT, 13B and 30B, and OPT-IML, Max 30B and Max 175B, were used, while for the MO models, internal pre-trained MO models, 5.3B, with modifications to the transformer model architecture were employed. GPU kernel implementations were based on Cutlass and Faster Transformer, with weight-only quantization GEMMs offering significant speedup in memory-bound cases. Multiple scaling factors per column were used in the quantization experiments. Section 4.2.1 Accuracy. In this section, we'll discuss the impact of quantization on the accuracy of various natural language tasks using different models. Our findings suggest that using 8-bit weight-only quantization doesn't significantly alter the accuracy when compared to the 16-bit floating point, FP16, format. This consistency is observed across different language tasks, implying that the models yield similar results. However, when we use 4-bit quantization with column-wise granularity, we notice a slight drop in accuracy. This is due to outliers in the weight distribution, which we've discussed in a previous section. To counteract this, we employ a group-wise quantization strategy, which maintains accuracy levels similar to the original FP16. We also conducted similar experiments for OPT-IML, a model used for machine translation. Our results, which are presented in a table, show the accuracy levels achieved with different bit quantization on OPT-IML 30B and 175B models. By using a group-wise quantization approach, we were able to maintain accuracy while reducing the bit size to 4-bit and even 3-bit for some parts. Next, we wanted to understand how our weight-only quantization speeds up matrix multiplication. We collected micro-benchmarks from OPT13B and OPT30B models and found that matrix multiplication can be sped up by up to 2.5 times when the number of tokens in the activation is small. This is typically the case for the auto-regressive part of language learning models, LLMs, which tends to dominate the overall runtime. We also conducted end-to-end benchmarks to calculate times for different input and output lengths for the OPT175B model on 8, 4, and 2 GPUs. Our results show that the context phase slows down, primarily due to running on fewer GPUs. Additionally, our weight-only quantization kernels have some slowdown for compute-bound cases. However, the time per decoder step is typically within 20% of FP16, even when using half or a quarter of the GPUs. The per-token latency doesn't scale with the number of GPUs since fewer GPUs need to communicate, and our kernels provide significant acceleration in the decoder phase. Finally, we calculated the throughput increase by assuming that the original FP16 model was divided across 8 GPUs within a single node and that the same node is used to serve int8 or int4 models. We measured the throughput per node by assuming that the model is replicated twice on the node for int8 and 4 times for int4, and that requests are served to the independent model instances concurrently. Our compression technique allows us to serve 4 instances of OPT175B on a single A100 node with 8 GPUs. Section Summary. The impact of quantization on natural language tasks using different models is presented in table, showing that 8-bit weight-only quantization does not significantly affect accuracy compared to FP16. However, 4-bit quantization with column-wise granularity leads to some accuracy degradation, which can be recovered by adopting a group-wise quantization strategy. Micro-benchmarks show that weight-only quantization can accelerate matrix multiplies by up to 2.5x for models with small activation token counts. End-to-end benchmarks demonstrate that the time per decoder step is typically within 20% of FP16, despite using fewer GPUs, and our compression technique allows serving multiple instances of a model on a single GPU node. Section 4.3 MO Model Performance Results. In Section 4.3, we delve into the performance outcomes of our weight-only quantization approach applied to a mixture of experts, MO, model. The results of our investigation are neatly summarized in the accompanying table. Our exploration spanned across various quantization precisions, starting from 8-bit and going down to 3-bit. Interestingly, we found that the MO feed-forward network, FFN, layers demonstrated a high level of resilience. This robustness allowed the model to maintain a high degree of accuracy, even when we reduced the precision to as low as 3-bit and 4-bit. This performance was comparable to the original accuracy achieved with 16-bit floating point precision. We also examined the overall speed enhancements achieved when we varied the batch size, using 8-bit and 4-bit quantization. The corresponding figure provides a visual representation of these improvements.